we've defined the notion of a projection onto a subspace, but I haven't shown you yet that it's definitely a linear transformation, nor have I shown you that if you know a basis for its subspace, how do you actually find the projection onto it? So let's see if we can make any progress on that here. So let's say I have some subspace. Let's say V is a subspace of Rn. And let's say I've got some basis vectors for V. So let's say these are my basis vectors. Basis vector 1, 2, 2, and I have k of them. I don't know what V's dimension is, but let's say it's k. It's got k basis vectors. So is a basis for V, and that means that any vector, not V, that's not V vector, that's V subspace. Now that means that any vector, let me call some vector, I don't know, let's say any vector A that is a member of my subspace can be represented. That means that A can be represented as a linear combination of these guys. So I'll make my linear combination, let's say it is, I don't know, y1 times b1 plus y2 times b2 all the way to plus yk times bk. That's what the definition of a basis is. The span of these guys is your subspace V. So any member of V can be represented as a linear combination of my basis vectors. Now, if I were to construct a matrix, let's make it an n by k matrix, whose columns are essentially the basis vectors of my subspace. So A looks like this. The first column is my first basis vector. My second column is my second basis vector. And I go all the way to my kth column, and I have k columns, is going to be my kth basis vector. If I'm going to have my kth basis vector, let me make the closing bracket the same color as my opening bracket. Just like that, it's going to have n rows because each of these basis vectors are members of Rn. Remember, V is a subspace of Rn, so each of these guys are going to have n terms. So this matrix is going to have n rows. Now, saying that any member of the subspace V can be represented as a linear combination of these basis vectors is equivalent to saying that any member A of our subspace V can be represented as the product of our matrix A times some vector y, where something was equal to A, for some y that is a member of Rk. Now, why is this statement and that statement equivalent? Well, you can imagine if you were to just multiply this times some vector y in Rk, so it's y1, y2, all the way down to yk, this is going to be equal to y1 times b1 plus y2 times b2, all the way to plus yk times bk, which is the same thing as this. So if you can always pick the right linear combination, you can always pick the right member of yk, so that you get the right linear combination of your basis vectors to get any member of your subspace V. So any member of my subspace right there can be represented as the product of the matrix A with some vector in Rk. And we don't know much about this vector right here in Rk. Now, the projection, let's say that x is just some arbitrary member of Rn. The projection of x onto our subspace V, that is, by definition, it is going to be a member of your subspace. Or, another way of saying it is that this guy, the projection onto V of x, is going to be equal to my matrix A, is going to be equal to, I'll do it in blue, is going to be equal to A times some vector y, for some vector y in RK. If we knew what that vector y was, if we could always find it, then we would have a formula, so to speak, for figuring out the projection of x onto v. But we don't have that yet. All I've said is any member of V can be represented as a product of our matrix A, which has the basis for V as columns, and some member of RK. That just comes out of the fact that these guys span V, that any member of V is a linear combination of those guys. We know that the projection of x onto V is a member of our subspace V. It has to be inside of V. So it can also be represented this way. Now, what was our definition of our projection? Our definition of our projection, we say, well, let me write it this way. We know that x can be represented as the sum of the projection onto V of x plus some member of V complement. Or maybe I could even write plus the projection onto the orthogonal complement of V, onto the projection of x onto the orthogonal complement of V. You could write it this way. I could have also written this as W, where W is a member of V complement. Actually, let me write it that way. That might make it simpler. I don't want to write too many projections here. Plus W, where W is a unique member of the orthogonal complement of V. Or you could say it this way. If you subtract the projection of x onto V from both sides, you get x minus the projection of x onto V is equal to W. Or another way to say it is that this guy right here is going to be a member of the orthogonal complement of V, right? Because this is the same thing as W. Now, what's the orthogonal complement of V? If we go back to this matrix here, I have V's basis vectors right here as the columns. So the column space of A is going to be equal to V, right? The column space of A is just the span of these basis vectors. And by definition, that is going to be equal to my subspace V. Now, what is the orthogonal complement of V? The orthogonal complement of V is going to be the orthogonal complement of my column space. And what's the orthogonal complement of a column space? That's equal to the null space of A transpose. Or you could also call that the left null space of A. But that we've seen that many, many videos ago. So we could say that x minus the projection of x onto V is a member of, let me write it this way, x minus the projection onto V of x is a member of the orthogonal complement of my column space of my matrix, which is equal to the null space of A transpose. That's the orthogonal complement of V. This is the same thing as the orthogonal complement of V. But what does this mean? What does this mean right here? This means that if I take A transpose and I multiply it times this vector, because it's a member of A transpose's null space. So if I multiply it times that vector right there, so projection of x onto V, then I'm going to get 0. I'm going to get the 0 vector. That's the definition of a null space. So let's write this out a little bit more. Let's see if we can algebraically manipulate it a bit. So if we distribute this matrix vector product, we get A transpose times the vector x minus A transpose times the projection. Actually, let me write this way. Instead of keep writing the projection onto V of x, what did we say earlier in this video? We said that the projection of V onto x can be represented as the matrix product of the matrix A times some vector y in Rk. That's where we started off the video. So let me write it that way, because that's going to simplify our work a little bit. So I'm going to distribute the A transpose times x, and then A transpose minus A transpose times this thing. This thing I can write as A times some vector y. And that was this is just a byproduct of the notion that the projection is a member of our subspace. Because it's a member of our subspace, it's going to be some linear combination of the column vectors of A. We saw that up here, so it can be represented in this way. So instead of projection onto V of x, I can just write A, y. This thing and this thing are equivalent because this thing is a member of V. And then all of that is going to be equal to 0. And then if we add this to both sides of this equation, we get that A transpose x is equal to A transpose A of y. Or, now this is interesting. Now remember where we started off here. We said that the projection onto V of x is equal to AY for some y that is a member of RK. If we knew what that y was, if we could always solve for that y, then the projection of x would be well defined, and we could always just figure it out. Now, can we solve for y here? Well, we'll be able to solve for y if we can take the inverse of that matrix. If this matrix is always invertible, then we're always going to be able to solve for y here, because we can just take the inverse of this matrix and multiply it times the left side of both sides of this equation. Now, if you remember, 3 videos ago, I think it was 3 videos ago, I showed you that if I have a matrix A whose columns are linearly independent, then A transpose A is always invertible. The whole reason why I did that video is for this moment right here. Now, what about our matrix A? Well, our matrix A has column vectors that form the basis for a subspace. By definition, basis vectors are linearly independent. So our matrix A has columns that are linearly independent. And if you watched that video and if you believed what I told you, then you know that A transpose A, in our case, is going to be invertible. It has to be invertible. So let's take the inverse of it and multiply it times both sides. So if we take A transpose A inverse, we know that this exists because A has linearly independent columns. And multiply it times this side right here, A transpose X. And then on this side, we're going to do the same thing. A transpose A inverse times this thing right here, A transpose A y. These two things, when you multiply the inverse of a matrix times a matrix, you're just going to get the identity matrix. So that's just going to be equal to the identity matrix. And the identity matrix times y is just going to be y. So we get, and this is a vector, so if I flip them around, I get that y is equal to this expression right here. A transpose A inverse, which will always exist, times A transpose times x. Now, we said that the projection of x onto V is going to be equal to A times y for some y. Well, we just solved for the y using our definition of our projection. We just were able to solve for a y. So now we can define our projection of x onto V as a matrix vector product. So we can write the projection onto V of our vector x is equal to A times y, and y is just equal to that thing right there. Y is equal to that thing right there. So A times A transpose A inverse, which always exists because A has linearly independent columns, times A transpose times x. And this thing right here, this long convoluted thing, that's just some matrix. Some matrix which always exists for any subspace that has some basis. So we've just been able to express the projection of x onto a subspace as a matrix vector product. So this says, so anything that can be any matrix vector product transformation is a linear transformation. And not only did we show that it's a linear transformation, we showed that, look, if you can give me the basis for V, I'm going to throw that basis into some, I'm going to make those column vectors equal to the column of some matrix A. And then if I take matrix A, if I take its transpose, if I take A transpose times A and invert it, and if I multiply them all out in this way, I'm going to get the transformation matrix for the projection. Now, this might seem really complicated, and it is hard to do by hand for many, many projections, but this is super useful if you're going to do some three-dimensional graphical programming. If you have, let's say you have something in, you have these cubes, let's say you have some, three-dimensional object. Let's say you have some three-dimensional object, and you want to know what it looks like from the point of view of some observer. So let's say you have some observer. Some observer's point of view is essentially going to be some subspace, right? You want to see what the projection of this cube onto the subspace, how would it look to the person who's essentially onto this flat screen right there? How would that cube look from this point of view? Well, if you know the basis for this subspace, you can just apply this transformation. You can, make a matrix with whose columns are these basis vectors for this observer's point of view. And then you can apply this to every vector in this cube in R3, and you will know exactly how this cube should look from this person's point of view. So this is actually a super useful result.